So hi, I'm Praveen, and I'm generally interested in making our programs more elegant, especially if they deal with uncertainty. And I kind of have a hidden agenda, which is to share the idea with everyone that there are a lot of commonalities between functional programmers and Bayesian statisticians. But I'm not going to go into the details of that. It's a hidden agenda after all. My concrete excuse for this talk is that we can do Bayesian inference by transforming programs. And I'm going to explain what that means, and I'm going to do that in two parts. And the first part, I'm going to describe the original algorithm by Shannon Ramsey that shows that this is possible, and then I'm going to describe the contribution of this work, which extends this idea to handle arrays and probabilistic programs efficiently. So let me set up some context. What is Bayesian inference? So imagine that you have an algorithm that you want to run to measure the running times of, and say it's an iterative algorithm, so you expect that the running time is a times n, where the a might be a constant cost per iteration, and n is the number of iterations that you ran it for. And perhaps there's some startup cost also for setting up variables and so on. So overall, maybe you have this linear model for the running time of your algorithm. So if you want to run experiments for a benchmarking algorithm, you might want to use linear regression, and it suits your purpose here, where you measure your running times for various numbers of iterations, and then you try to fit a line through these points, and the slope of the line will tell you b, and the a will be the other way around. So that's well and good, and I just want to clarify that this work that I'm going to talk about today isn't really tied to measuring algorithm running times or linear regression whatsoever. It's just an example for showing Bayesian inference. So what we really want to do is Bayesian linear regression. So what's the difference between these two methods? Well, if there's one main difference, well, in the linear regression case, we observe a bunch of points, and then we try to fit the best line that fits through these points. And in Bayesian linear regression, we actually measure the points again, but we want to get an estimate for different kinds of lines that fit in various degrees on these points. So we want a distribution over lines for the same observations. So what does that mean? Well, how do we get a distribution over lines? Well, the first step is to write a generative model. And this step is actually scary for a lot of people, but I think it should be kind of comforting for this audience. I mean, a generative model is basically a place where we declare our beliefs about the world, about how we think the world works. It's very declarative. How cool. And we say, OK, fine. So before even running the algorithm many times, maybe we have some prior beliefs about the costs. I mean, we wrote the algorithm, right? So maybe we think that the costs are centered at certain values symmetrically. So maybe we want to use normal distributions to model these costs. So that's good. So this model that I've written is itself a distribution. And it's a larger distribution composed of two smaller ones, normals. And it's composed. I mean, it's compositional. I mean, isn't that exciting? And we can see on the right-hand side that we can sample values from this distribution. And you can see some lines on the right. And you may have to squint a little bit to see the lines are actually different. But trust me, they're different. So fine. So we wrote down a model for how we think the two costs are distributed. What about the running times? Well, we already thought about the running times being linear functions of a and b. So we could model it that way. But wait, look at the right-hand side. I mean, these are too perfect. We don't expect running times to follow such perfect values in the real world. So maybe we want to add some noise. So we can add some normal noise to our k measurements of our running time. And finally, we have a generative model that looks a little bit reasonable. We think the world works this way. Great. So on pen and paper, we did all this. We have a model for generating bunches of possible worlds. What's the next step? Well, the next step is to actually go out into the real world and run our algorithm many times for different iterations and collect a bunch of data. So wait, so we have a model that gives us different possibilities of running times and slopes and y-intercepts. And we have the real data that we observed in the real world. So can we use the real data that we observed to update our prior beliefs about how costs are distributed? Well, that's the essential question of the inference step, which is the third part of this process. We want to know which lines are likely to produce this data. So with what we have right now, I can already describe a sort of simple approach for getting this distribution of the lines conditioned on data. So we can use the generative model that we have and generate a bunch of different possible samples, where each sample basically has k measurements and a line. And then we can use the observed data to reject all the samples where the running times don't match what we actually observed, and keep only those candidates where the running times actually match what we observed. And amongst these candidates that remain, we can analyze how the lines vary, and there we have it. We have a distribution of lines conditioned on the data that we observed. And as a quick aside, this process that I just described isn't the most efficient way to do this. There's actually a whole research area dedicated to how to do this in an efficient way. But you might ask, OK, fine, that's really cool and all, but this is ICFP. Why do we care about this? And it turns out Bayesian inference is actually very compositional, and we can compose different inference methods using smaller reusable building blocks. Composability, I mean, reusability, isn't that exciting? Isn't that what ICFP is about? So the key idea to doing this in a composable way is to treat distributions as programs. And today I'm going to focus on one transformation that we call Desintegrate that transforms programs to do the Bayesian step of what we call conditioning. So the first step is to replace these guys with programs. And don't worry about what these programs mean right now, but the basic idea is that the input program actually represents a generative model that we saw earlier. And the output is a function which, when given the data that we observed, produces a program representation of the distribution that we care about. So let's look at how Desintegrate works. And actually, let's look at how Desintegrate works with just two measurements, not k, because the steps will be too long, unfortunately, in this method. So OK, fine. So let's look at disintegration. The input is this monadic-looking program that uses return and bind to compose a program that represents distributions, denoted by this m, over measurements, two measurements, and a line. And this language is something we call core Hakaru. And it's kind of Haskell-like for those who are familiar with that. So that's the input to Desintegrate. And we already know that the output is supposed to be this function that returns, that when given observations, returns a distribution over lines. Great. So all we have to do is fill in this middle stuff. Well, for this middle stuff, we can take a step back and think about what we're trying to do here. In the input program, these measurements y1 and y2 can take an assortment of values. But we're interested in restricting ourselves to that part of the distribution where y1 and y2 take the values t1 and t2 that we observed. So we do this sort of restriction by using this funny left triangle symbol function called constrain. So calling this function basically means constrain the values of y1 and y2 to be the observed values t1 and t2. And constrain works in the context of a heap, which we can think of as a state which contains the variable bindings and which variables have been constrained and which variables are supposed to be inferred. And this heap changes throughout the disintegration process. So how is constrain built? How do we define that? What does it even mean to constrain a pair of measurements? Well, we define constrain for every program language construct. And for details, I actually encourage you to look at the paper about how constraint is defined. But more specifically, constraining a pair of measurements leads to two recursive calls to constrain. One to constrain y1 to be t1, and the other to constrain y2 to be t2. Maybe this recursive definition for this audience is not that surprising, which is a good thing if it's not. So now we're left with the question, what does it mean to constrain y1 to be t1? Well, y1, if we look in the heap carefully, is bound to the normal distribution. So perhaps the question is, what does it mean to constrain this normal distribution to be t1? And that's equivalent to the following question, which is, how likely is it to obtain the value t1 from the normal distribution? So the answer to that is the density of the normal distribution at t1. So constraining y1 to be t1 is equivalent to replacing the binding in the heap for y1 with a factor binding for the normal density. And this updated heap is passed to the second call to constrain that we still have to do, which is to constrain y2 to be t2. So this follows in the same way. Constraining y2 to be t2 results in replacing the binding for y2 in the heap with a factor for the normal density at t2. And this is the final heap that we're left with. And the final step of this disintegration process is to absorb this heap into the final output program. And now, as a quick aside, you might be wondering, why does this heap have these funny variables with bars on it, and why is it colored differently? Well, the gist of it is that we found it useful to distinguish between two languages, one being the input-output of Disintegrate, and the other being the internal language of disintegration. And for details, again, I highly encourage you to look at the paper. But more importantly, we have this output program, which answers our original question, which lines are likely to generate the data that we observed. And the answer is the lines that exactly follow this distribution and approximately follow this distribution. So this is great. To summarize, we started with a program that makes two measurements, which led to two calls to constrain, and which led to an output that has two factors. We can extrapolate from this process for the original question that we cared about, with k measurements, an arbitrary number of measurements, and which will lead to k calls to constrain, which will finally result in an output that leads to k factors. And this is the original algorithm, and it works, and it's correct. But this is bad. I mean, we're basically saying that the size of the output program, as well as the time it takes to produce it, is linearly dependent on the amount of data that we observe. And maybe we want to observe a lot of data, and this is not good. And let me also remind you that disintegration is supposed to be this reusable building block that we use again and again in a long pipeline of transformations. And producing these long programs is going to make downstream transformations pretty unhappy. And personally, I also care about interpretability of the output programs, especially when we're doing Bayesian analysis. And long, huge programs are not very interpretable either. So this old technique I'm going to call unrolled. Basically, it seems like we're unrolling the bindings, all of them, into the heap. And it pleases neither computers nor humans. But no worries. We have an extension to this technique, and that's what I'm going to describe now. And I call this lifted, and we'll see why soon. But the idea is that now we can condition arrays in probabilistic programs independent of their size. So it takes one call of constraint and one factor in the output. So let's see how we do that quickly. So the first step is the input to the disintegrate. And at the first step already, we see some changes. So in the old program, we had k bindings in the input program, which becomes one binding in the new input program. And we achieve this by using a constructor called plate. And plate is basically a generator of arrays. And it takes a size for the array, and it takes a function, which is basically like an indexed distribution, which we use for generating each array element. And it returns a distribution of arrays from which we can sample different arrays. And note that, so this is the first time we're even talking about arrays. Like earlier, we were approximating arrays with k tuples, but now the language is extended with plate as well as the type of arrays. So fine, so the input program changed a little bit. How about disintegrate? How does that change? Well, the first step of disintegrate in the old case should be now familiar. We just start with constraining the value of the tuple, k tuple, to be t in the context of the heap. And the first step doesn't really change in the new method either. We constrain the value of y, the variable y, which happens to have an array type, to be t, okay, in the context of the heap. So what's next? Well, again, in the old method, we already saw that constraining a k tuple led to k calls to constrain. What happens in the new method? Well, we're trying to constrain the variable y, which is bound to a plate expression in the heap. So what does it mean to constrain a plate? Well, we not only have to add the definition of plate to constrain, but we actually have to change constrain in a fundamental way. And we do so in two steps. The first step is that we parameterize the calls to constrain by a list of index variables. And I'll describe what that means. But what the result of that is that the k calls to constrain that would have happened in the unrolled approach become one parameterized call to constrain. Similarly, the k bindings on the heap also become one parameterized binding in the lifted approach. And when we do this parameterization, we call it lifting. And that's why the name lifted disintegration. So we lift two things. We lift constrain, and we lift the bindings on the heap. And lifting bindings allows us to have succinct output, and lifting constrain allows us to perform disintegration in short time. So in the old approach, we now chug along and make k calls to constrain. But in the new approach, we have one parameterized lifted call to constrain that conceptually makes k calls, and so on. And with each call in the old output, we produce a new factor on the heap. But in the new approach, the one lifted call to constraint produces a lifted factor on the heap that conceptually represents all k densities that would have happened in the old approach. And the final step of disintegration is to absorb the resultant heap into the program. In the old approach, the heap is huge, so the output program is also huge. In the input program, the new approach, the heap has lifted bindings, and we can concisely express lifted bindings using plate. So great, we've started on a journey where we're basically able to condition arrays symbolically without depending on their size. So what kind of programs does this work for? To remind ourselves, our representation of index variables was variable and the size of the array. So this represents iteration spaces, and this basically allows the program to work for observing whole array manipulations, so like copying, transforming, transposing, mapping, etc. And this is already useful for a wide variety of programs. I urge you to look at the paper for more details, but we tried this method out for a set of benchmarks from the R2 probabilistic programming suite. We also want we have a lot of future work as well. We would like to extend the representation of index variables so that we can condition on some parts of the array and for others. And similarly extend index variables so that we can have conditionals inside arrays. And finally, we'd like to move up from something like plate, which assumes no dependencies among array elements, to something like chain-like dependencies between array elements. So that's it. I mean, I hope I've managed to share with you the idea that it's not only possible, but kind of fun to do Bayesian inference via equational reasoning on programs. And I highly encourage you to look at the original paper that talks about this, as well as especially this paper for fun details about conditioning transformations. And for other transformations that I really didn't have time to talk about today, I ask you to look at our Hacker website for more details. Thanks. I'll take questions at this point.